Okay, so I want to go through page 33 notes, and this is going to help us for homework 16, which is going to deal with graphing the, well, really it's the inverses of exponential functions, which is a logarithmic function or a log function. And I'm going to go back to what it means to be an inverse. And if I look here on the board, I do have the graph of e to the x, right? E to the x goes through 0, 1, has a horizontal asymptote of y equals 0, and then it's increasing exponentially by powers of e. I want to then sketch the inverse of this function. And even if I don't know what that function is, I do know that any function and its inverse will always have a line of symmetry with the line y equals x. So I drew that in yellow. So the thing is, every x and y value switch. So 0, 1 will now become 1, 0. So whatever this inverse function is going to be, it'll have to go through that point. It'll have to go through 1, 0. And the other thing is that since this was y equals 0, and we're switching the x's and the y's, now it's going to be x equals 0. So there will be a vertical asymptote on the inverse of whatever this e to the x is. And we sort of mirror this shape across the line y equals x. So it's going to look something like that. So the green shape, which is the reflection, and maybe I'll highlight that just so it comes up just a little bit clearer. So this shape right here is our shape of every function that's an inverse of an exponential function, which we'll call a logarithmic graph or a logarithmic function. This, remember, was the shape of an exponential function. Now, we need to keep track of both of them and keep kind of their characteristics separate in terms of which one has which feature, right? So like a exponential graph has a horizontal asymptote, and a logarithmic graph has a vertical asymptote. An exponential graph, it's that y-intercept I'm after. In a logarithmic graph, it's the x-intercept. So that's going to be the toughest thing about this particular, these particular two sections. Okay, so I want to actually take a look at, so what is the inverse of an exponential function? It's a logarithmic function. And so there are several different ways that we can write these. And again, you should be familiar with this from last year. There's the natural log, which is base e. There's common log, which would be base 10. And then there's just any other base, but just generically log base b. And you can always get the inverses by doing that log, whatever the base is of this particular number. So, for example, 2 is my base for the exponent. 2 is going to be the base for my logarithm. So if I do change of variables, so x equals 2 to the y, I'm going to log both sides, but the base I'm going to choose is base 2. So I'm going to log base 2 of x is equal to y. There should always be a correspondence between that base and the base of your logarithm. Okay? And like logging both sides, it's kind of like square rooting both sides, like adding 10 to both sides, f inversing both sides like we did earlier. So this would be the inverse function, and then you just rewrite it using the language of f. F inverse of x equals log base 2 of x. So if you raise things to the power of 2, the operation that undoes it would be taking the logarithm base 2. Here I have base 3, but there's other things going on here. That's okay. I still need to do a change of variable. So call this like x equals 3 to the y plus 1. You would log both sides, but this time base 3. So we'd have log base 3 of x is equal to y plus 1. That allows me to get y at least out of the exponent. Now I need to subtract 1. And I'd be really careful because when you subtract 1, it's after you've done this logarithm. So you might want to do log base 3 of x, like in parentheses, minus 1 equals y, or our inverse function, f inverse of x. Okay? Now, if your value is outside the exponent, so like minus 4, when you do your change of variable, because that minus 4 is outside the exponent, I need to add it over to the other side first before I do the log of both sides. So it would be x plus 4 equals 10 to the y. Now that I've got that isolated, so to speak, I can log both sides, and it'll be base 10. And log base 10 of the entire expression, x plus 4. And you can leave it as log base 10, perfectly fine, but you might also see it as just log without a base number. And when you see that, you should realize that if there's no base there, it's implying 10. It's called the common log. And I guess common just from the fact that our number system that we do normal operations with is base 10. So if you're in base 10, you don't have to necessarily put the 10, and it'll be assumed it's the common log. Okay? And then part D, it's already, at least the base is isolated, so I can do log of both sides, base 4. So x equals 4 to the negative 2y plus 5. Now I'm going to log both sides, log base 4 of just your x is equal to negative 2y plus 5, and then isolate the y. So I would subtract 5 first, so log base 4 of x, and it's just the x, minus 5 equals negative 2y, and divide by negative 2. So that this much of it right here would be your inverse function. And, I'm not going to put a huge emphasis on the inverses, other than you should have a good idea of how you can go from one to the other by either logging or taking the power to undo whichever operation you have. The base of your exponent, so that 4, always corresponds to the base of your logarithm, in this case, which was 4. Okay, so that's part of today's lesson, is looking at that. Okay, the other part of today's lesson is to look at what is the parent function, again, kind of committing this shape to memory. And remember, we've graphed that shape. That shape was this function here, right? It's the inverse of an exponential function. And so we want to know what that parent function looks like, and know the characteristic things that come with that parent function. A vertical asymptote and an x-intercept of 1. And then you just start applying any kind of transformations. The transformations act the same. So when I see a negative in front of the function, all of the y's switch, so that's a reflection over the x-axis. If there's a negative in the x's, all of the x's switch, therefore it's a reflection over the y-axis. Okay. So if I see this, I'm recognizing the parent function as a log function, so I will sketch this. I will draw a vertical asymptote at x equals 0. Okay? And that's one thing maybe that you remember last year in Honors Advanced Algebra. You cannot take the log of 0. And the reason you can't take the log of 0 is because logs are the inverses of exponents, and an exponent can never give you 0. So if you cannot ever get 0, then working backwards, you can never input 0 into its inverse. So that's the vertical asymptote. And then we also have a x-intercept of 1, 0. And we draw our graph. So it's going to hug the asymptote, and then it's going to take sort of a sharp right turn. And we want to go ahead and plot like 3 points. And just like yesterday when we graphed powers of e, natural log, which is the base e, is going to have very strange numbers too. Like I could think about putting 2 and then be like whatever ln of 2 is, or it might be best to put in e, since that's what it counts powers of e, and the natural log of e is 1. And I could put in e squared, because the natural log of e squared would just be its exponent value, which is 2. So it's kind of like, again, thinking about the exponent graph backwards. Powers of e now become the x, because they used to be the y. And there's our sketch. This image, if I did negative ln x would be these exact same points, but with a reflection, since all of the y's are changing, a reflection over the x-axis. So that graph, red, there we go, of still a vertical asymptote at x equals 0, and instead of this characteristic increasing shape, it'll sort of hug the asymptote up here and then go off in that one, in that direction, I should say. I take a sharp right turn. And so then this is still 1, 0, but now when I put in my powers of e squared, because of this negative in front of the function, all the y values will be negative. So this would be e negative 1, and this would be e squared negative 2. Okay. Again, part C, we've seen this transformation before. If I want to do the x's as negative, just reflection over the y-axis. Doesn't affect the vertical asymptote. Still x equals 0, and I'm going to look for that on Tuesday's quiz. So make sure you're labeling that as x equals 0 because it's a vertical asymptote. If it were a horizontal asymptote and the exponential functions, remember those are y equals, so make sure you have the correct letter. And then again, instead of going up in this direction, we're going to go up and to the left. So we hug the asymptote until we get to the intercept, and then we take kind of a sharp left turn. This value right here is negative 1, 0. And then we start putting in negative e1, because there's already a negative there. And then we put in negative e squared, in this case would be 2. Now I think, I have no, does this say log base, I can't even see what that says, log base 8, log base b? I don't know exactly what that says. So let's say it's log base 8, I have no idea. But the key is that this is a negative and this is a negative, so we need both reflections. So our image then still is going to have a vertical asymptote at x equals 0. But then, again, thinking about this negative reflects it over the x-axis, and this negative reflects it over the y-axis. So our image is actually looks something like this. Where that value right there is negative 1, 0. And then I'm not sure what that value is, but you could also plot the points to see what that looks like. Okay, so I think that's good for the first video. What I want to do next is also walk through example 4 and then example 5. But by all means, if you would rather try some of these on your own and then check the video, that's fine too. But I will go through those step by step in the next video.